Okay, so we're going to start with the recitation section. We wrote out just sort of an outline of what we're going to go over today, so hopefully this stuff is useful to you. If not, feel free to stick around, but either way. So we're going to go over 3 general topics. First is going to be just some basic proof techniques that could come in useful for the homeworks. Linear algebra is going to be sort of vectors, what they are, dot products, cosine similarity is something that will come up, basic matrix operations, linear independence, and finally eigenvalues and eigendecompositions of matrices. And then Manan will cover some useful probability stuff as well. So any questions before we get started? All good? Cool. Awesome. So feel free to stop me at any time if you have questions. Otherwise, I'll just sort of breeze through. OK, so the first thing for proof techniques is proving what are called universal statements. All that this really means is proving a statement of the form any something has some property. So for example, any even number is a multiple of 2. That's by definition, so that's not really something that will be interesting to prove. But something that could be interesting to prove is something like every square of an odd number is odd. Square of an odd x is odd. And the reason we're looking at this is just to sort of see how you'd prove something like this. And the way you would do this is by taking an arbitrary element and then proving that sort of what you want holds for that arbitrary element. And so in this case, we would say, assume that we have some element x which is odd. And now we're going to say, what can we do with the statement in order to get to our conclusion? So we can write x as 2 times some number m plus 1. And this is just sort of by our assumption that x is odd. And now we're going to say, what do we know about x squared? This means that x squared, and I'm going to skip to the conclusion here and let you guys work out the details, but x squared is equal to 2 times 2 m squared plus 2m plus 1. And what does this mean? This means that x squared can be written as 2 times some number plus 1. And that's exactly what it means for a number to be odd. And so what we did here was we just took an arbitrary element of the type that we wanted, said let it be any odd number, and use those properties to arrive at our conclusion. All good so far? Cool. OK. And then you might see me putting this at an end of a proof. That's just sort of called a tombstone. That means that we finished our proof and we've shown what we wanted to show. OK. Now, what if we wanted to disprove some sort of statement like this? So here we had to prove something for every number that is odd. If we wanted to disprove a statement of the form for every number some property holds, we just need to show one example. As long as one example is a counterexample, we've shown that the statement is false. So for example, if I want to say every square of an odd x is even, which is obviously wrong because we just proved that that is true, I wouldn't have to actually draw out a proof. I would just have to say, like, think of x equals 3. X equals 3 is odd. Its square is 9, which is not even. And so I have a counterexample, and the statement is false. Cool. So that sort of covers our first topic, universals. Just take an arbitrary element and show your conclusion. Questions so far? Awesome. OK. Now, contrapositive is when you have a statement of the form something implies something else. So if A is true, then B is true. You can prove this sort of directly in the first way, which is you assume that A is true, and then you have to show that B is true. Or you can show it by contrapositive. And this just relies on the fact that A implies B is the same as not B implies not A. This is the symbol for not or negating a statement. And this looks a little confusing if you haven't seen sort of logic written out this way before, but it's actually, I claim, really intuitive. So let's say the statement A is there's a snowstorm, and B is school is canceled. So the statement here would be, if there's a snowstorm, school is canceled. Now, say that I come up to you and say, hey, school isn't canceled today. Immediately you would know that there is no snowstorm, because if there were, school wouldn't be in session. And so what you've really done there is you said, since school is not canceled, there is no snowstorm. Does that sort of move make sense? Cool. Okay. And so this is called contrapositive. Awesome. The next thing that we're going to go over is proof by contradiction. And proof by contradiction sort of is taking a statement that you want to show is true, assume that it's not true, and show that the results then don't make sense anymore, that it leads to a contradiction. And what this means is that your assumption that you made had to be false. And in particular, the statement had to be true. So this is, again, sort of roundabout, but it's actually very useful. And a really common example of this is prove that the square root of 2 is irrational. What does it mean to be irrational? It means that you can't write the square root of 2 as a fraction with whole numbers on the top and the bottom. So we said we're going to prove this by contradiction. So proof, you might see this sometimes. I don't actually write it, but it's useful to see. For the sake of contradiction, assume that root 2 can be written as m over n for some whole numbers m and n. Now we're going to show that this leads to a contradiction, and so this assumption can't hold. What we do here is we square both sides. We show that 2 is equal to m squared over n squared. And in particular, this means that 2n squared equals m squared. Okay, how does this show that the result, or that the assumption can't be true? Well, m squared has to have an even number of prime factors. Why is this true? So m has some number of prime factors, and then when you square that, that number of prime factors is repeated. Okay? So there's an even number of prime factors on this side, then hopefully there should be an even number of prime factors on this side. Otherwise, what we wrote down doesn't make sense. Now look at n squared. By the exact same reasoning we just applied, n squared has to have an even number of prime factors, which means that this side, with the addition of 2, now has an odd number of prime factors. So we have an odd number of prime factors equals an even number of prime factors. That's a contradiction. And that means that our initial assumption could not be true. And so our assumption was false. And that concludes the proof. So just to reiterate, it's a pretty simple idea. If you want to prove something, assume the opposite is true. And if you show that that leads to nonsense, the initial thing actually should hold. Cool. OK, we have one last proof technique that we care about, which is induction. Before that, in the recitation notes, which we'll send out later, we also mentioned proof by cases. This is pretty intuitive, so I won't go through an example, but it's just saying that if you have something you want to prove for example, all numbers, you can break it down into cases and prove it for each case. For example, if I wanted to prove something for all integers, I could first prove it for even integers, then prove it for odd integers, and that concludes the proof. Cool. OK. So the last proof we're going to do is by induction. I'm going to move down here. OK. So I'm assuming some of you have seen induction before. This is actually a sort of interesting application of induction for a fact that's usually proved in a different way. So we're going to prove that the sum of all numbers up to n, of all counting numbers up to n, is equal to n times n plus 1 over 2. OK. Now, I haven't really explained how induction works yet. So what induction does is sort of building a recursive program for your proof, for those of you with a background in computer science. And so what you do is you prove this in a very simple case called the base case, same as in recursion. And then you sort of make this move called forming the inductive hypothesis, which is assume this conclusion holds for sort of small versions of the problem. If that is true, I can show that it holds for bigger versions of the problem. And since you've shown it for the smallest version, i.e. the base case, you can just repeat that argument to show it for bigger and bigger versions of the problem. And by induction, it holds for everything. What does that look like here? So our base case is going to be n equals 1. And now, for n equals 1, the sum of all numbers up to n is just 1. And we can just verify this by plugging in n right here. We have 1 times 1 plus 1 over 2 equals 1 times 2 over 2, which equals 1. So our base case checks out. OK. Nothing super interesting going on there. Now let's look at our inductive case. The way this works is we say, assume that 1 all the way up to n sums up to the thing we want it to. What we want to show now, we will show that 1 plus everything up to n plus 1, the next bigger case, is equal to n plus 1 times n plus 1 plus 1 over 2. So that's what we want to show. And if we can show this, we just apply this reasoning forward from the inductive case, and then we'll be done. OK, so how can we show this? Well, let's break apart this 1 plus all the way up to n plus 1 like this. We have 1 all the way up to n, and then we tack on an additional n plus 1. So by our assumption here, called the inductive hypothesis again, this part of the sum is equal to this expression. And then we're going to tack on the n plus 1. And now, via some algebraic manipulation that's, I guess, not super important, you see that this is now equal to n plus 1 times n plus 2 over 2. And this will work out. So we would say, actually, why don't we just write it out so I make sure I'm not lying. OK. Here we're going to have n squared plus n over 2 plus 2n plus 1. And hopefully this works out. So this equals n squared plus 3n. Sorry. This should be plus 2. N squared plus 3n plus 2 over 2. And now this should be the same as that expression up there. Not 100% convinced that I didn't make a mistake, but the idea should still stand. OK, so that covers sort of the last of our proofs. Just as a note, there's a different version of induction called strong induction, where instead of just assuming something for n and then showing it for n plus 1, you can actually assume it for all values from n to smaller n. And then you can use that the same way. So if for some reason here I need to show that actually the sum of 1 up to n over 2, or if I needed to use the sum of 1 up to n over 2, I could do that by just saying, assume this result holds for sort of all n smaller than the n that I'm trying to prove the result for. That's called strong induction. OK. Any questions so far before we move on to linear algebra? Awesome. Great. So for linear algebra, like I said, we're going to start with vectors. Hopefully, people have seen this before, but if not, it's not super complicated. OK. So a vector, for our purposes, is basically just a list of numbers. So usually we say we have a vector v and then we write it in terms of its components. So v1 is the first entry in the list, also called the first component. Then we have the number v2 up to however long our vector is, vn. So for example, if v was just 1, 2, 3, that would be a length 3 vector. OK. Now, the way that we find lengths of vectors should be familiar from sort of high school geometry in the case of two-dimensional vectors, but it generalizes to higher dimensions. So the length, also called the norm of a vector, which is written this way, is just the square root of the sum of the squares of each of the components. And so in 2 dimensions, you might have seen this as the Pythagorean theorem. Right? If we have sort of a vector there, and we write it out as this much in this direction plus this much in this direction, we have that c squared equals a squared plus b squared. So c is the square root of a squared plus b squared. It's the same idea. OK. The next useful operation on vectors that we care about is called the dot product. Now, intuitively, I think the best way for us to think about dot products is as ways of comparing two vectors. So let's say we have one vector u1 through un and another vector v1 through vn. An important note here is that to take the dot product, your vectors have to have the same length. We then say that the dot product u dot v is just equal to the product of each of the components, and then you sum all of those up. A nice way you can sort of picture this is you kind of stack these two vectors together, take the product. So I have v1 times u1, vn times un, and then I just sum across that whole vector. That gives me the dot product. A nice property of the dot product is that the norm of a vector is actually just the square root of the dot product, or the norm of a vector squared is the dot product of the vector with itself. And you can check this for yourself. It's not super hard. Basically, if you take a vector and multiply it with itself, you get this sum. And if you take the square, you get the square of this same expression. Oh, sorry. The square of this expression is equal to that sum. OK. Any questions? Cool. The next property that is important for us is that you can compare two vectors using what's called cosine similarity. And that just uses the fact that the dot product between two vectors u and v is actually the same thing as the norm of u times the norm of v times the cosine of theta, where theta is the angle between u and v. So if I have u and v, and this is theta, dot product is the cosine of this angle. And what does this mean? This means that we can define a measure of similarity between vectors called cosine similarity. And what it is it's just the dot product over the product of the norms, or the sizes of the vectors. And just by sort of moving this over to this side, you can see that this is the same as the cosine of the angle. Now, why is this a measure of similarity? Well, the cosine of an angle is 1 when the angle is 0. If the vectors were pointing in complete opposite directions, the angle would be 180 degrees. The cosine of that is -1. And so, yep, question?
Sorry, this is about, like, in the homework, when they wrote the norm, they had like a little subscript 2. I was wondering, like, what does that denote? Is that different than the norm here? Or
no, that's the same. Okay. The reason for that is that you can have norms sort of in other geometries. The 2 just means basically that here we're raising everything to the second power, and then we're taking the square root. If you had like a subscript 1, all that would mean is I don't raise things to the second power, and I don't take the square root. And depending on the subscript, just the norm changes.
Cool, thank you.
Yep. Awesome, cool. So we're done with vectors. we'll move on to matrices. So a matrix is kind of just a grid of numbers, again, for our purposes. So for example, we can have a matrix A of, let's say, 4 numbers, and often you'll see them written down like this. But in general, it can be any size grid of numbers. So a matrix is just a grid of numbers. And for our purposes, these numbers will always be real numbers, so no complex numbers or anything like that. Cool. Questions? Okay. Okay. Now, the way that you add two matrices is super intuitive. If I just have a matrix A plus a matrix B, and I'm just going to use this 2 by 2 size example to make the operation clear. If I have this, I'm just going to add each of the components. Components meaning, again, sort of individual numbers in the same slot that they appear in either matrix. So again, for matrices to add them, they have to have the same size. And so the result is going to be the sum of these two slots, the sum of those two slots. And I realize I'm writing really small, so I apologize for that. Okay. Awesome. And again, this generalizes to larger sizes, hopefully pretty clearly. Now, something more interesting is the matrix product. There's a lot of ways to think about the matrix product, but sort of one nice way to think about it is sort of as using the idea of a vector dot product. So let's say we write it out in terms of two matrices, again, of the same size. The way I'm going to take the product of these two matrices is as follows. I'm going to, first of all, build a matrix with the same number of rows as this matrix and the same number of columns as this matrix. So here, those are all equal, so it'll be a 2 by 2 matrix again. And when I say 2 by 2, the first number is the number of rows, the second number is the number of columns. So if I said 2 by 3, it's 2 rows, 3 columns. Okay. So what I do now is for this first entry, it's the first row and the first column. So what I do is I take the first row of A and multiply it as a dot product with the second column of B. Okay. And so this is going to take actually some room to write. But what it's going to end up being is A11 times B11 plus A12 times B21. Does everyone see how that works? Cool. Again, stop me at any time. OK. So now what about first row, second column? It's going to be the same pattern, except now I'm multiplying it by the second column of B. And so I'm going to have A11 B12 plus A12 B22. And I won't fill out these guys. Hopefully it makes sense. What I'm going to do here is I'll do the same thing, except now using the second row of A. Now, for me to multiply A and B as matrices, they don't actually have to be the exact same size. All that needed to be true is that the number of columns of A, i.e. the size of this vector, and the size of this vector were the same. So the way we notate that is if A has m times k as its dimension, meaning m rows and k columns, B has to have k rows and some number n columns. So the really easy way to remember this is that these middle numbers have to match up for me to be able to multiply these as matrices. Now, another just generally useful thing that you might need to use in homeworks is if I want to look at the ijth entry in the product AB. What this means is in the ith row in the jth column. What I do is I sum across sort of the number k, or maybe to use a different index, I sum across L from 1 to k of A ik B kj. Now, really what this is saying is, again, just repeating the dot product argument. I'm saying, now look at the ith row of A and sum across all of the k things in there multiplied with the jth column of B. It's kind of the same idea. Okay. Now, the next, let's see. The next matrix operation we care about is the transpose. So A transpose is just the same thing as flipping rows and columns. So if A, again, was 1, 1, 1, 2, 2, 1, 2, 2, the transpose of this switches these two. And since these are on the diagonal, they stay the same. And now A doesn't have to be square anymore. Even if A is sort of long or skinny or wide, I can still sort of flip A like this, and that's still a valid transpose. Some properties of transposes are that A transpose is the same thing as A. That makes sense. I flipped it once, and then I flipped it back. If I take a product AB and transpose it, that's the same thing as sort of flipping the product and taking the transpose of each of those. This is not obvious, but if you're interested, you can look up a proof. It's not hard to find. And then the other property is that if I sum two matrices and then take the transpose, I can just think of transposing them immediately and taking the sum. Okay. The next idea is a matrix inverse. Now, to understand a matrix inverse, I'm going to have to introduce one special matrix, which is called the identity. So we write I. The identity matrix is a matrix that has ones along the diagonal and zeros everywhere else. So the identity is a square matrix, but again, it can be a square of any size. The inverse of A is a matrix A to the negative 1. We just say A inverse. And it's a matrix that has this property, that A times A inverse is the same thing as A inverse times A, and that's the identity. If you want to think about this in sort of analogy to numbers, the inverse is kind of like the reciprocal of a number. You multiply it with the initial number and you just get 1, the identity. Okay. The properties of inverse are kind of similar to the properties of transpose, in that A inverse is the same as A, AB inverse taken as a whole is the same as inverting B and then multiplying it by the inverse of A. And finally, the transpose of an inverse is the same thing as the inverse of the transpose matrix. So it doesn't matter if you take the inverse first and transpose it or do it the other way around. Okay, super important fact about inverting matrices. Not all matrices have inverses. Only special matrices do. There's a theorem that we're really not going to talk about at all, but it has to do with the determinant. A matrix is invertible if and only if the determinant of the matrix isn't 0. If that doesn't mean anything to you, that's fine. Okay. But yeah, so important thing, not all matrices have inverses, and you have to be a square matrix to have an inverse, because for this product to equal this product, they have to have the same size in either way, so the matrices have to be square. Okay. Super quickly, some types of matrices. And these, I think, are more for just everyone to be on the same page in terms of notation. I can build a diagonal matrix D by saying diag of some list of numbers. Let's say the numbers are D1 all the way through Dn. And this gives me the matrix D1 down to Dn on the diagonal, and zeros everywhere else. So for example, the identity matrix I wrote up there is diag of a bunch of ones. And these matrices are called diagonal matrices. A triangular matrix, not super unintuitive again. It's a matrix that has some non-zero entries on its diagonal and above, but then everything under the diagonal is 0. This is called upper triangular because everything above the diagonal is non-zero. Or sorry, not everything above the diagonal is non-zero. Things under the diagonal are 0. Up here you can't have zeros, but it can also be non-zero. So this is called upper triangular. You can, of course, have a lower triangular matrix where the roles are just kind of flipped. Everything above the diagonal is 0, and then under the diagonal you can have whatever you want. Okay. The last two kinds of matrices that we're going to have are symmetric matrices. So symmetric here means sort of symmetric to this transpose flip that we were doing. So a matrix is symmetric. The easiest way of defining it is this way. If A sub ij is the same thing as A sub ji in any entry. And so what that means basically is that if I have a matrix with some things on the diagonal, then I have some number A here, it has to appear here on the flip. If I have a number B here, it appears here. C here appears there. And then on the diagonal, I can have whatever I want. Finally, an orthogonal matrix is a matrix U such that U transpose U or U transpose is the identity. Okay, so again, looking at this, we can see that U has to be square. And what does this mean? We won't really show this, but what this means is that every column of U as a vector has a dot product of 0 with every other column of U. And what this means is that the vectors are at 90 degrees to each other, or they're orthogonal. The way you can see that is by thinking again about the cosine of the angle as sort of telling you what the dot product is. Okay, so these are orthogonal matrices. So every column is orthogonal to every other column except for itself. And similarly, actually, every row is orthogonal to every row except for itself. Okay. So the final thing we're going to talk about is eigenvectors. But before that, there's an important concept of linear independence. Linear independence is a property that can hold of a set of vectors. So say that I have vectors v1 up to vn. These, I'm going to abbreviate, are linearly independent if the following holds. This equation for some numbers that I can choose, a, equals 0 in the sense of the 0 vector, so the vector where every entry is 0, only for all of the a's equal to 0. So they're linearly independent if this holds only for a1 equals everything up to an, and all of these are identically 0. Okay. Now, intuitively, what this should sort of mean, and it's not intuitive until you sort of learned about this a little bit, but this means that all of these vectors sort of point in kind of different directions in whatever space they're in. And if you have vectors that are linearly independent, you can obtain any other vector as sort of sums of those vectors with certain coefficients. Okay. Another way of saying that these vectors are linearly independent is by saying we have a matrix V where I put these vectors as columns in the matrix. So this is the same as this matrix gives us the only solution to this is x equals 0. So this is related to things like rank nullity, if that rings any bells. But this is just sort of a way of thinking about this property in terms of matrices rather than just sets of vectors. Okay, so last thing is going to be eigenvectors. Okay, so what's an eigenvector? Let's say I have a matrix A, then I have a vector x. X is an eigenvector if the following property holds of this product. If for some scalar number lambda, that's what this means, a times x is just sort of a scaling of x. So the picture that this should give you is I have my vector x pointing in some direction. I multiplied it by a. And instead of just moving x somewhere, which is what generally multiplication does, it actually just either extends x or shortens it or flips it the other direction and extends it or shortens it in that way. Okay. So these are interesting for us mainly for one reason, but first some important properties I guess you should know about eigenvectors. So if we rearrange this expression, we get ax minus lambda x equals 0. And this is the same as a minus lambda times the identity matrix times x equals 0. And we're not going to do this, at least I don't think, in this class. But the way you find eigenvalues, which are the values lambda such that there exist vectors such that this holds, is by solving this equation. And the way you solve this equation would be by taking the determinant of this matrix and setting it to 0. So we can solve by solving determinant of a minus lambda I equals 0. This is just, I guess, a note that I should mention, and I realize I haven't defined determinant. And that's fine because we really shouldn't ever be worrying about this in the class. Okay. So what are some properties of eigenvectors? First of all, if we have a vector that satisfies this, there's actually a whole sort of family of vectors. So I can take x and take some scaling of x and put it through this multiplication. And it's going to also give me this property. So let's say I have x as an eigenvector. If I take a times some constant times x, I can pull this constant out. And this is going to be c times a times x. So this is going to be c lambda x. Or in other words, this is lambda times my initial vector cx. So what does this mean? This means that I want to be able to make some sort of canonical choice about which of these eigenvectors I want to use, right? Because I can take an eigenvector and scale it, and any of those works. So the choice we're going to make is we're going to choose x such that the norm of x is 1. And this is just going to be nice for us because we're going to say all our eigenvectors have sort of unit length, and then we can think about what happens to those eigenvectors. For example, a unit length eigenvector here now is a lambda length vector when you put it through A. Another property, so this is the first thing. The other one is that if A is symmetric, and I'm going to put here in parentheses and real, but like I mentioned, we're not dealing with complex numbers. If A is symmetric and real, then all the eigenvectors are real. In general, they're not guaranteed to be all real. Or sorry, the eigenvalues are real. And also, we can choose our eigenvectors to be orthogonal, or they're going to be orthogonal. And we have eigenvectors and orthogonal should remind you of the thing that oh, there it is, put over here. Orthogonal means that the dot product of two things is 0. That's sort of actually why we call those matrices orthogonal. So what this means is that different eigenvectors of A, when you dot product them together, are 0. And actually, since we've chosen to say our eigenvectors have norm 1, when you dot product them together, their dot product is 1. And why is that true? It's because of this. The dot product of something with itself is just the square of the norm, and we've chosen the norm to be 1. So that's nice. Dot products of different eigenvectors for symmetric matrices are 0. Dot products of the same vector is 1. OK. So very last thing is we're going to use this property to talk about the eigendecomposition of a matrix. So if we have an n by n matrix, i.e. a square matrix, such that its eigenvectors are linearly independent, this means that I can write the matrix A as the following matrix multiplication for some special matrices. I can write it like this, where P is going to be the matrix of eigenvectors. So if I call my eigenvectors v1 up to vn, P is this matrix. And D is the diagonal matrix of the corresponding eigenvalues. So zeros off the diagonals, all of these entries are the eigenvalues. So in particular, v1 times A should be lambda 1 times v1. Vn put through A should be lambda n times Vn. And for all the vectors in between, this holds as well. OK, so I mean, this is kind of a curious fact. Not super clear why it's useful for us at the moment. Well, one reason it's useful is that it's easy for us now to exponentiate matrices. So say I wanted to calculate A squared, or in other words, just A times itself. What happens if I expand my definition of A? Or not my definition, but how I've written A. OK. Notice that here we have a P and a P inverse. Since these are inverses of each other, these go away and they just become the identity. So in particular, I can just ignore them, but I'm going to write it here. Anything times the identity is itself. So I can just ignore that identity and say that, for example, I multiplied D by I, and it gave me D back. So this, at the end of the day, is P D squared P inverse. So the reason this is nice is that to exponentiate A, or to take a power of A, I don't actually have to do anything with P. The only thing I have to do is take a power of D. The reason that is nice is that a power of a diagonal matrix is actually the same thing as just taking the power of the entries along the diagonal. And so in order to do this multiplication, I actually barely have to do any work at all. It's O of n, right? I'm just going along the diagonal, exponentiating, or taking powers of each of these, and then after that, it's not O of n anymore because I have a matrix multiplication. But that step is super easy. OK. So note that we can do this when we have A such that the eigenvectors are linearly independent. So it's not super obvious if I just give you a matrix if you can do this or not, right? You would have to find the eigenvectors and be like, oh, are these linearly independent or not? So the very nice note is that this holds for any real symmetric matrix A. Now, why is this true? It's because all of the eigenvectors of a real symmetric matrix are orthogonal. In particular, orthogonal vectors are linearly independent. And so if I give you a real symmetric matrix, you know that there is some matrices that you can use to write it like this. Why would this be useful for us in class? Well, think about, for example, the case that A is an adjacency matrix. An adjacency matrix for an undirected graph is going to be symmetric, right? If there's an edge from U to V, there's an edge from V to U. And so it might happen that you want to do some math on an adjacency matrix, and you know that because it's symmetric, you can write it like this. And so taking powers of it is actually going to be very easy. OK. Any questions about that? Yeah.
Could you go over what P is again, like the V1 through Vn?
Yes, for sure. So hopefully I have enough room to write here. But these vectors V1 through Vn are just the vectors such that A Vi equals lambda Vi. Or sorry, lambda I Vi. And the lambda i's are along this diagonal in this matrix. So in particular, it's just the matrix whose columns are all the eigenvectors of A. Cool. Just a small additional note here. In this case, P is orthogonal because all of its columns are orthogonal. And that's what we said in orthogonal matrices before. And this means that P inverse is the same thing as P transpose. So for a real symmetric matrix, doing this is actually even easier. This P inverse becomes a P transpose. And that is just by the definition of an orthogonal matrix. The inverse is the same thing as a matrix transposed. OK. Awesome. Any more questions? Great. Well, like I said, we'll send this out as part of the review sheet. But I'll turn it over to Manon to talk about probability.
Awesome. Erase some stuff.
Oh, yeah, I'll help you do that.
Get to that later. Fine. Awesome. So in terms of probability, we're going to be covering some of the fundamentals. The ideas are going to be initially some basics, then inclusion-exclusion, the union bound, which follows pretty much directly from inclusion-exclusion, conditional probability and Bayes' rule, random variables, expectation and variance, and then a couple inequalities that will be useful. So if you have any questions, just like Vasco said, please feel free to stop me and ask me. This is 100% for you to make sure that you understand what you'll need for the coming homeworks. So to begin at the very basics, the sample space of a certain set of events is given by omega. And so let's say, for example, we're considering a dice roll. So our sample space here would be 1, 2, 3, 4, 5, 6, which represents all of the possible outcomes of a given event. So if you want to, for example, denote how the possible outcomes of a dice roll being less than 4, the subspace of that sample space would be 1, 2, and 3. And if you want to look at all the even events or even possibilities, we'd have 2, 4, and 6, etc. The probability of a certain event defined on this event space is a function that has a couple of properties. It maps the event space to real numbers on the between 0 and 1, and or rational numbers between 0 and 1. And it has two properties. The first of which is that the probability of all of the events sums to 1. And the second of which is that the probability of A union B is A B for A and B disjoint. What this basically means is that we can define two sets, set A and set B, that are both subsets of our universal set omega. And if these sets are disjoint, that is, they don't share any overlapping elements, we can sum their probabilities, and that's the same thing as the probability of the union. Does that make sense so far? Sweet. They should all be ideally review. So using the couple of notions of probability and the basics that we defined earlier, we can actually do a couple of interesting things. The first thing that we're going to like to do is compute the probability of the union of two subsets of our entire event space where the subsets are not disjoint. So that basically means computing P of A union B, where A intersection B is not equal to the empty set, right? So what you might have seen earlier in other classes is like, let's say you have two event spaces, or event subsets A and B, and there's some sort of overlap, and this overlap is a non-empty set overlap. Right? It's not necessarily clear immediately how to do this. I'm sure you remember from a while ago that this looks something like PA plus PB minus P of A intersection B, right? Basically what we're doing is we're going to add over the probability of A and the probability of B and then subtract the overlap. What's interesting is you can also define this and identify this formula from some of the first principles of probability. In particular, what you can say is that we can write this, the probability of A union B, as we can first take the probability of A without B. So this basically means this is like the set minus notation. So this corresponds to this. This is this subset of events that are in A but not in B. We can then add the probability of the events in B not in A. So that corresponds to this. So far so good. And then add the probability of A intersection B. So this corresponds to this, and then the last, this corresponds to this, right? And then what we'll have to do here is we can do a couple, one interesting trick, which means we can add and subtract P of A intersection B. Right? Clearly, if you add and subtract the same thing, the equation stays the same. And now what we notice is that, we only have black mark. Well, I guess we have a red marker. That might be helpful. Is that if you take A without B and add A and B, that gives you all of A, right? If you take this whole thing and you add the intersection of A and B to A without B, you get all of A. So this gives us P of A. The same thing is true for B without A and A and B. So here if you take these two, that gives you this whole thing, and that gives you P of B. And then finally, you have this last term minus P A intersection B, and that remains. And you'll notice these are the exact same formula. This is kind of how you get the principle of inclusion-exclusion for two sets. There's a more general version of this that extends to n sets, and we have this when we'll state it in our notes for you in case you want to spend some more time deriving it or looking at how you'd extend this to multiple sets. We also have a proof sketch. It's by induction in case you have any interest in proving that for yourself as well. The formula there is slightly more complicated, so I can write it down really briefly, and if anybody has any questions, we can go through that. But I don't think you should have any. If you don't get it, I don't think you should worry too much about it. So basically, the general form is I is 1 to k, where we have subsets x1 to xk. We can write this as the sum over 1 to k, where this is not the empty set, -1 to the I minus 1. So this looks pretty scary. We started off with that and we somehow ended up here. It's definitely non-trivial to get this from this. This is also in the notes, so if you don't understand it immediately, there's a little bit more intuition of how we get here from here. The general idea is we can start pretty simple. If we set k equal to 2 and we look at this, you can pretty much derive for yourself that you basically get the same formula as you would have up there. All that we're doing here, and in general, the general intuition is we're going to start by adding all of the sets by themselves, so x1, x2, x3, all the way to xn. then we'll subtract the intersections of pairs of 2, then add back pairs of 3, subtract pairs of 4, etc., etc. And the overall intuition is that we want to make sure that we don't double count any part of our overall thing. So here we wanted to make sure we didn't double count the intersection between A and B. And in general, this formula gives make sure that you don't double count between some k number of sets. Again, you won't have to worry about this too much, but it's just here for your own edification if that's interesting to you. The next thing that we're going to look into is what's called the union bound. And this sounds a little bit intimidating at first, but it's actually really simple. And the general idea is that if you want to compute the probability of the union of some number of sets, so let's say we have n sets, so I is 1 to n, ai, yeah, just make it x, xi. This is less than or equal to the sum from I equals 1 to n of the probability of all of the sets. Basically what we're saying here is that if you want to get some sort of upper bound on the union of the probabilities of, or the probability of the union of some number of sets, you can simply add the probabilities of each of these individual sets. The intuition behind this and why you might immediately think this is true is that back at the principle of inclusion-exclusion, we added the sets and then we subtracted their intersection to make sure we didn't double count it. Here all we're doing is just not subtracting the intersection. So that's like where this less than or equal to sign comes from. And we have equality here if all of the x's are mutually exclusive, that is there's no intersection, so we don't actually have to worry about subtracting anything. And this holds true. In the notes that we'll send out, there's a proof of this by induction. If that's interesting to you, you can definitely look into it. But the general intuition that we have here, and the one that I think is important to understand, is that all we're doing here is not worrying about all the intersections and overlaps and just dealing with the sum of the probabilities of all of the xi. Does that make sense to everybody? Does anybody have any questions so far? Excellent. So let's move on to the next thing. This is a little bit more complicated and definitely really fundamental in machine learning in general, and it's the idea of conditional probability. There's an easy way to motivate this. So consider, for example, that we want to compute the probability that we're tossing 3 coins. And let's say we want to compute the probability that all of our tosses land heads. Right, so the immediate answer is 1/8, right, because each coin has a probability of landing heads of 1/2, and these are independent events. So we can just multiply 1/2 by 1/2 by 1/2 and get 1/8. But then let's say I told you that the first coin already landed heads. And the question is, what's the probability that all of our coins are head, conditioned on the fact that the first coin is already heads? Right, so let's say we have coin 1, coin 2, and coin 3. And I'm already giving you the information that coin 1 is heads. Now what's the probability that all of our coins are heads? Well, we only have to worry about these 2 coins. And the probability of this being heads is 1/2. The same thing for this one. And we get 1/4. So that's the intuition behind conditional probability. The idea is that if we have some information that we already know, how can we incorporate that into our overall computation of probability? Before we go into that, one other thing that I wanted to make clear is the notion of independence. So if you have 2 events, they are independent if the fact that one event happened does not affect the probability that the second event happens. So what I basically mean by this is that let's say you have 2 events. One is the outcome of a dice roll, and the second is the outcome of a coin toss. These events are independent because clearly the outcome of the dice roll has no implication on the outcome of the coin toss. The interesting thing, however, and the thing that is important to know, is that mutually exclusive events are dependent events. What I mean by this is that let's say that we have a set of outcome spaces of 1 to 6, like we had in our dice roll example earlier, and our events where x1 being 1, 2, or 3 being rolled, and x2 being 4, 5, or 6 being rolled. If x1 is true, then x2 is necessarily false. So these events are dependent in the sense that the outcome of x1 affects the outcome of x2 happening. Does that make sense to everybody? So independent events, to summarize, are events that have no implication on each other, and dependent events are events that have implications on each other. Mutually exclusive events are events that share no common elements in their subspaces, and mutually exclusive events are dependent events because if one event happens, the second event does not happen. The probabilistic way to write that event event A is different from is independent from event B is the probability of A given B is the probability of A. Now what I mean by this is that if B happened, it doesn't give us any information about whether A will happen. Is that clear so far? Right, so given the information about whatever the outcome of B is, our outcome of A stays exactly the same. The probability of that happening is exactly the same. And this also implies that the probability of A and B is the probability of A times probability of B. So these are two results that are true for events that are independent of each other. The next thing we're going to describe is Bayes' rule, which is kind of the foundation of conditional probability problems. And generally, if you see conditional probability occur in a p-set problem, it's going to be important to, at some point, use Bayes' rule. And so, again, we're going to consider two events. Let's say event A and event B. And they're both, obviously, part of our overall event space. And the definition of Bayes' rule is that we can define the probability of A conditioned on B as the probability of A and B over the probability of B, which you can also write as a probability of B given A, the probability of A over the probability of B. Does this make sense so far? Basically, what Bayes' rule tells us is that we can describe the probability of A given B in terms of some concepts that we already know, how to compute the probability of A and B and the probability of B. And what's interesting about Bayes' rule is it allows us to do a lot of interesting computations about this, given things that we can traditionally compute in a more easy fashion, stuff that we already know about. So one very instructive example that I think is used a lot, but is still pretty interesting, and so I think it's worthwhile going over, is the example of like an event that is not necessarily event with low probability happening with, well, actually, let's just go through the example. So the example is that suppose that 1% of women who enter a clinic have breast cancer. So 1% of women have breast cancer. And a woman with breast cancer, so woman with breast cancer, has a 90% chance positive result. And a woman with breast cancer, or a woman without breast cancer, has a 10% chance of positive results on the test. Now, the question we'd like to compute for any given patient is, let's say that a woman, let's say that we're given that the person who has taken a test and they have a positive result. The probability, we want to compute the probability that this person has cancer. Right? And the reason this is kind of interesting, and even like in a real world standpoint, is it's important to understand that, if you design a breast cancer test that has a 90% accuracy, this might seem very high. It might seem like it's, it's important and it's ready to be deployed in the real world. What we can do is, given just this information, we can compute this probability. And what we want to see is we want this probability to be very high. If the test is positive, we want the probability of cancer to be very high. We want this test to be very accurate in reflecting the information. How we can write this is, moving over back to this board in this form, we can write P of BC given positive tests as P of positive given BC times the P of BC all over the P of positive. So far, so good? Does this equation make sense from that problem? So this is what we have so far, and what we'd like to do is compute this. We are given the probability of positive given breast cancer, right? If the woman has breast cancer, the probability of positive results are 0.9. So we already have this number. We're also given the probability of breast cancer. 1% of women have breast cancer. So we already have this number. The question then is to compute, how do we compute the probability of a positive result? We don't have that information directly from that information. What we can say, however, is the probability of a positive result is equivalent to the probability of a positive result given breast cancer times the probability of breast cancer plus the probability of a positive result given no breast cancer times the probability of no breast cancer. Does that make sense? What we're effectively doing here is we're marginalizing over the event that this person has breast cancer. So what we're saying is that this first term says, what's the probability that the result is positive given that they have breast cancer, times the probability they have breast cancer. So that's the event in which the person has breast cancer. And we're summing that with the probability that is positive given that they don't have breast cancer, times the probability of them not having breast cancer. So that, in total, sums to the probability of it being positive. Because there are two instances in which the result can be positive. The person has breast cancer or the person doesn't have breast cancer. And we sum over both these instances to get what the probability of the positive result is. Does that make sense to everybody, how we compute the denominator? And now we have all this information from that as well, so we can just simply compute the denominator and the numerator. And what we actually get is 8.3%, which is really bad, right? The idea that our test, given that the test is positive, the probability that you only have cancer is 8.3%, is not a good, it means that the test isn't really a good reflection of the person having breast cancer or not. So that's kind of an example of how Bayes' rule can be used with limited information to give us a pretty surprising result. For a test that is 90% accurate, given these numbers, it seems pretty unlikely that the person, given that the test is positive, actually has breast cancer. So that's kind of the intuition and application behind Bayes' rule. All right, we're going to move on now to random variables. These might be a little bit more confusing, so I think it's worth spending a little bit of time on them. A random variable x is defined as a variable that can take on different values depending on the outcome of some probabilistic process. Now what I mean by this is that, let's say for example, we define the random variable x to be the number of coins that come up heads, after we toss 3 coins, right? So the value of x is this, which depends on some probabilistic process. Clearly, x is not always one value, because as we toss 3 coins, x might be 0, 1, 2, or 3. We can then define something interesting. Let's say we want to compute the probability that x is 0. Well, this is simply the probability that after we toss 3 coins, we get none of them as heads. And the answer to this is clearly 1/8. So a random variable basically is a variable whose result depends on some probabilistic process. And this provides us a lot of, I guess, tools or framework to analyze some interesting questions in the future. A random variable in and of itself, let's just take away these things. We're just considering some random variable x. And it can take on either a discrete range of values or a continuous range of values. So in our previous example about the random variable corresponding to the number of times we see heads in 3 coin tosses, that's a discrete random variable because it can either be 0, 1, or 2. In contrast, there might be a random variable that takes on a continuous range of values, and that would be a continuous random variable. And we can define a PDF and a CDF for a PMF and a CMF, we can define a PDF and a CDF for a discrete random variable. Now a PDF, so let's say that we define fx as the probability mass function probability density function for a random variable x. Now what this means is that fx defines the distribution of x over all of its possible values that it can take. So for x being the number of heads that are tossed, that are obtained after 3 coin tosses, fx would be f of 0 is 1/8, f1, f2, f3, 1/8, 3/8, 3/8. So basically, f defines the probability distribution of all the possible outputs that x can take. Does that make sense? The analogous function for a continuous random variable is the probability mass function, and this would be some sort of continuous distribution over the possible outputs they can take. And a PDF and PMF both must satisfy certain properties. In particular, for a discrete random variable, so let's consider x discrete random variable, then we must have the following things. We must have that f of x is greater than or equal to 0. We must have that the sum over all possible x's of f of x is 1, because the probability over all possible outcomes must be 1, must sum to 1. And the final thing we must have is that these are the only 2 real conditions, right? So f of x must be greater than or equal to 0. You can't have a probability that's negative. And also, if you sum over the probabilities of all of the outcomes that x might take, the probabilities must sum to 1. Analogously, for a continuous random variable, we have that f of x must be greater than or equal to 0. If you integrate from negative infinity to infinity of f of x dx, you get 1. Basically the same exact thing as if you sum over all of f of x, you get 1. Here we just replace the sum with an integral. We can also define the cumulative distribution function, or CDF, for a given random variable x. And the CDF basically is denoted by an uppercase F, and it represents the probability that the random variable is less than or equal to some fixed value. So here, little x is some fixed value, and what we're trying to express is the probability that a random variable has a value less than the fixed value. So how would we express this? What we can actually do is we can just write f of x is the integral from negative infinity to x of f dt. Basically what we're saying here is that we're summing over the probability of all the values that are less than this some fixed x. In the continuous case, in the discrete case, we just replace the integral with a sum. Does that make sense so far? The CDF is just defined as the sum of probabilities of all events that are less than some fixed, this is a fixed constant x, and here our fixed constant x, we're just integrating over all the probabilities. Are we clear so far what a PDF and a CDF are? Sweet. This also means that you can obtain the PMF by differentiating the CDF because of the definition of the CDF. Does that make sense? So those are kind of interesting identities. You can integrate the PMF to get the CDF, and you can differentiate the CDF to get the PMF. Sweet. Okay. The next thing we'd like to cover is expectation and variance of random variables. So expectation answers the question, let's say you have a random variable that can be some random variable x. What we'd like to answer, or the question we'd like to ask is, what is the expected value of this random variable? That is, like, what value do we expect it to produce as output given some number of throws or some number of times this event has occurred? And we can define the expectation. We write it as e of x. We write that as the sum over all values x times the probability that the random variable is equal to that value. Does that make sense? It's basically a weighted average of all of the outcomes x can take with respect to the probability of that given outcome. Again, for a continuous distribution, if f(x) is continuous, we can obviously integrate in the exact same way as the sum and get x times f of x dx, where f of x is our probability mass function, and x is, again, the value. So again, it's just a weighted average, but instead of being a discrete weighted average, we have a continuous weighted average. Expectation has a couple of interesting properties that I guess I won't get the chance to prove, but one of the most fundamental ones is called linearity of expectation. So let's say you have two random variables, x and y. There is no condition. X and y can be dependent. It doesn't matter. All we really need is that we have two random variables, x and y, and we can express the expectation of their sum as the sum of their expectations. This is super useful because this is a third random variable z. Z is x plus y, and we have no idea what the distribution of z is. But we can break this down into e of x plus e of y, and now we can solve this because we know what the distributions of x and y are. Does that make sense? It's really important to remember this because almost any problem that random variables come up, linearity of expectation comes in handy to help solve that problem. The variance of a random variable v of x is the expectation of this quantity, squared, which we can also, this is a little messy, let's write that again. We can also write as e of x squared minus e of x squared. This follows directly from this. If you just expanded this and simplified, you would get this. There's no complicated math happening there. Basically, what the variance is saying is that we want the expected value of the how far away any given value x is from its expected value. Does that make sense? So we're just kind of quantifying how far x is from the expectation over all values of x. And this is what the variance is defined as. It's normally written as var, actually. A crucial thing to note is that this is not equal to this in all cases. But this is true if x and y are uncorrelated. Now, we're not going to define that. We're not going to describe correlation or discuss it at all. Basically, something you might want to know, something that might be interesting, is that independent variables are always uncorrelated. So if x and y are independent, then this is true. uncorrelated variables aren't always independent, but that's a whole separate topic. Basically, if x and y are independent, then var x plus y is equal to var x plus var y. If they're dependent, this is not true. Awesome. And there's a bunch of special random variables that might be interesting and might show up in different problems, and they all have names. So hopefully some of these names sound a little bit familiar, but if not, we can go through them anyways. A Bernoulli random variable. What else? A geometric. A uniform. And a normal. Now, a Bernoulli random variable is a random variable with parameter p, and it describes or can be interpreted as a coin flip with a probability p. So what we're saying here is that the flip lands heads with probability p and tails with probability 1 minus p. So the only parameter for a Bernoulli random variable is p. The expectation of a Bernoulli random variable is e of x is p, and the variance var of x is p times 1 minus p. Does this sound familiar? Awesome. The next thing is a geometric random variable. Now, suppose you keep flipping this coin with probability with the probability of p of being heads, and you want to understand how long it will take or how many tosses it will take until this random variable lands heads. That's what a geometric random variable describes. And if x is drawn from Bern with p, if x is drawn from so this also has probability of p. If x is drawn from geometric p, then we have that e of x is 1 over p, and the variance of x is 1 minus p over p squared. The derivations for this are also in the notes and should be also online. So if you have any questions about that, feel free to ask on Piazza or just do them by yourself and see if you can make some sense out of why these things are true. Basically what this means is, let's say we have a coin that lands heads 1/10 of the time. The expected number of times it would take for us to obtain a heads after tossing this coin for some number of times is 1 over 1/10 equals 10. That's what this basically means intuitively. Does that make sense to everybody? Sweet. The next thing is uniform random variable, which is a continuous random variable where we have f of x is 1 over b minus a for a less than or equal to x less than or equal to b, and 0 otherwise. On a graph, that would look like if we have a and b, the mass would be like some fixed value here and 0 everywhere else. And we have the expectation and variance for the uniform random variable on the sheet we'll send out. And for normal random variable, again, I'm not going to write out the formula. You can kind of look this up anywhere. But this is what you see as the normal of mu and sigma squared. The expectation is mu, and the variance is sigma squared. That's why you see n mu sigma squared, because these two things parameterize the normal distribution completely. So these are kind of 4 really important distributions. You'll see them a lot. We're running out of time, so I'm just going to state some of the inequalities for you to see briefly. These inequalities are pretty important just to set some bounds. So in some problems you'll be doing in your problem sets in the future, you might want to start with some of these inequalities and then use some of the properties we described of random variables to simplify to form that might be interesting to you. So Markov's inequality states that the probability of some random variable being greater than or equal to a is less than or equal to the expectation of that variable over a. Chebyshev states that, well, it's just Markov for the variance. So basically this states that the probability of x minus e of x squared is greater than or equal to a squared is less than or equal to, well, actually, let's write the second form because that'll be more instructive. And then we can call it probability of basically, this helps you determine the probability that either x or x minus e of x is greater than or equal to some fixed value a, and it lets you bound that by the expectation or the variance of that random variable. The proof for this one is actually relatively straightforward. We have 1 minute, so I can write it down really quickly. You can write this as Basically, this is saying that the expectation of x is the probability you can split x into two events, A and not A. And if A is true, times the probability of A being true, plus A not true, the probability of A being not true. And then all you got to do is, let's just say this is 0, and then you get the inequality. Basically, what I'm saying here is that you can define the expectation as the sum of these two things. And if you let this be 0, this is strictly greater than or equal to the resulting expression. And then you can divide through by A, and you'll get Markov. If that didn't make sense, I'm sorry I went through it really fast. It'll be a little bit more detailed in the notes that you'll see. Hopefully that'll make some more sense. And in general, these two inequalities help you bound the probabilities by some value, expectation or variance of the random variable that hopefully you'll either be able to compute or you'll have by definition from the set of random variables that we've defined for you. So hopefully this has been useful. If you have any questions, either ask us on Piazza, ask us afterwards, or just read through the notes that we'll send out shortly afterwards, and hopefully that'll be instructive as well. And yeah, let us know if you have any questions. Thank you.